Okay, I think it worked. Yeah. All right, we're recording. So in particular, we'll be looking at implementation, common implementations of a lot of these structures, and the most common operations on them. So I won't really cover how the operations are implemented, but I will cover just in general how they work and also the cost of them. We'll be talking a lot about time complexity. Where's my thing? There it is. Okay. So I've tried to structure this in a way that's sort of like an intuitive order. So we'll start with like some very basic ones that I would consider fundamental. These are like not really built on top of any other structures. They're just their own sort of things. And then the more complex ones are built on those fundamental ones. But before we get into that, today we are mostly going to be talking about time complexity. So I should actually define that. Again, this will probably be a review because I think you tend to learn this pretty early on in your classes. But time complexity is just a general measure of an algorithm's performance with respect to the amount of data it's operating on. So in general, we will say the variable n is like the number of elements. The number of elements in some structure, in an array, in a tree, in whatever. And then when we talk about the time complexity of something, for all of our purposes, we will be using what's called big O, which is like the average amount of time it takes, because algorithms are very complex. So sometimes there are edge cases where it'll be super fast or super slow, but we're just concerned with the general case. And the thing inside the parentheses here will be some power of n. So we'll have like n to the x, where x is an element of the natural numbers. Like, no, it can also be 0. So just an integer, a positive integer. So if it's 0, of course, that means we have O of 1, which is constant time, which means that whatever this operation is, it happens in generally a quick amount of time, but more importantly, just without any relation to the number of elements. So for example, something that we'll see very shortly is getting any element from an array is an order 1 operation. It's a constant time. It doesn't matter how many elements are in that array. You can always just go right to that element. The other ones we'll see order n. So like if you are looping through an array and printing everything out, you have to go through n elements. So that's order n. And we'll see, we won't see n squared. The other one we'll see is log n. And this is sort of implicitly in computer science. Whenever we say log, we are saying log 2, log base 2. And we'll see this a lot with trees. So that's sort of like a more formal definition. I like to think of this graphically, where we have the number of elements, so n on the x-axis, and then just some measure of the time, t, that it takes to complete an operation for that number of elements. So for a constant time operation, we'll just have a flat horizontal line because it doesn't vary with n at all. For a linear time operation, so order n, this will just be like y equals x, or t equals n in this case. So order 1, that's order n. And then for log n, just have your typical sort of logarithmic curve there. And there are more, which we will look at when we start talking about algorithms instead of data structures, because these numbers get bigger. N squared is very common. In log n is common as well. But the point of showing it graphically is that it sort of makes clear the point that we are only caring about their behavior at infinity. We are using the order, this big O notation, to say, if I have an operation that is order n time, in general, as n approaches infinity, for any arbitrary n, it will take longer because its value of t will be higher than one that is O log of n. And same for constant time. So this is just sort of a rough way of comparing different algorithms. Now, it's important to note that whenever we use big O notation, constants and like everything other than the highest power of n is dropped. So if we have order of 2n plus 5, whatever that means, that's just order in. Because again, we are only interested in the behavior at infinity, not the particular line. It is very, very important to note, and they don't ever really talk about this, at least from what I've been taught, that these are not the same thing. An algorithm that runs in 2n plus 5 times is, a little over twice as slow as an algorithm that runs in order n time. At infinity, they're the same, because an n squared algorithm will always be slower than 2n plus 5, and a log n one will always be faster. But I mean, 2 is a non-negligible constant there. So this one runs twice as slow as this one, but that's more of an optimization thing, and it's not super useful usually when you are comparing two different algorithms, at least at this level. Okay, so that's time complexity. A similar thing exists called space complexity, where when n is the number of elements, t will be, instead of measured in like seconds or some arbitrary time unit, it'll be measured in bytes usually. So for an array, if I have n elements, then my size complexity will be, or space complexity will be order n, because for each of those n elements, I store however many bytes it takes to store one element. Whereas if I was storing something that had sort of like additional data structures, like caches or something, then that would be a bit higher. We won't be talking about that really, but just in case I mention it, that does exist, and they're basically the same thing. The important thing, I think, is to just get the graphical visualization down. That's the thing that really helps me. Oh, I lost my cursor. Okay, so we will start by looking at the fundamental types. I avoided calling these primitive because primitive is usually used for like types, like int, float, long. But these are like basically the atoms of data structures. You can't get much simpler than this. So we'll be looking at array, which everyone knows, linked list, which everyone, or at least most people know, and tree, which most people probably also know. Okay, so with an array, and I'll be making connections to what we talked about in the previous couple of lectures as well. So an array is a contiguous block of memory. So if I have an array of 5 elements, 6 elements, you can just draw it like this, where they are all together in memory. And because they are stored contiguously, they are random access. Random access is sort of just a shorthand way of saying that getting any arbitrary element in the collection is constant time. So that's our first sort of thing here, is get on an array is order 1. Now, the reason that it's order 1 is because all an array is it's a chunk of memory that's contiguous. But what we have in the code, if we have like int r, and say that's 5 ints 1, something like that, then what r is a pointer to the first element. So when we say, give me r at 2, it just takes this pointer, increments it by 2 elements, which is just math. That's a constant time operation. And then we go straight to this element. So order 1. And again, that only works because these are stored contiguously in memory. And because of that, arrays are also very good for things like cache coherency. Because if you have an array, a lot of times it's assumed that you will want multiple elements from that array all around the same time. Like the most common thing you do with an array is loop over it and do something to each element. And because they're all stored right next to each other in memory, it's very cache friendly. They're all right there. They just sort of reduce the number of RAM accesses that your CPU has to make. So in general, when you are looking for a data structure that is very simple, just doesn't need to store things in any particular order, an array is usually the best bet. The sort of downside of the simplicity, though, is that some of the other operations, which are very common in certain cases, don't really work that well with an array. For example, inserting is average case order n. And there are quite a few things to say here. The first is that if I have my array of 6 elements here and I want to insert one at the end, all I have to do theoretically is just tag one on the end there, right? And that's constant time because I don't have to like I just go straight to the end of the array. I can get a pointer to there with just some pointer addition. That's just math. And then I put a value there. So that's one case where I'm adding to the end. In general, you will be, the big O notation means the average case. So in general, you have to assume that you'll be adding to any location. Yeah.
I mean, I don't know. The big O means worst case.
O is big O worst case? Maybe so. Okay. It doesn't really matter. I guess worst case is even better to think about because you want your things to run as fast as possible. So if you optimize for the worst case, then they're guaranteed to run as fast as possible. What's the average case? Is that
omega?
Omega? Theta. Okay. Okay, sure. Oftentimes those are the same. I think actually for all of these that we'll be talking about, the worst case and the average case are the same, except if it's like an edge case like here, where if I insert particularly at the end, that's constant time. But usually comparing best, average, and worst is done when you're looking at algorithms, because those have things where, like, if you feed a sorting algorithm a particular sequence of data, it's going to take like n squared. It's just super slow when normally it's n log n. But anyways, thanks for the correction. Okay, so if I'm inserting at the end, that's constant time. But in general, just assume I'm inserting somewhere in here. So say I want to insert at the first index. So I want to shift everything else down. Well, I have to move all of these elements down by one because it's stored contiguously. I can't just insert something in and overwrite what's there and not move everything else. And so if I'm inserting at the beginning, which is the worst case, the big O, then I have to shift all in of my elements to the right by one. Okay. The other thing is, even if I'm adding right to the end, there's no guarantee that my array has this amount of data. It might not have that allocated. My array might be exactly 6 bytes on, we'll assume on the heap, because on the stack, you actually cannot resize arrays. You traditionally, like, you shouldn't. And so what that means is I have to, I can either insert something there, which is undefined behavior, if my array is not allocated that block of memory, because at that point, this could be being used by something else, and I just overwrote the first element of whatever else is there. But if I, am aware of that and I account for that, I still have to go to the heap or the free store, request a bigger chunk of memory. That deals with the operating system. That's super, super, super slow in the context of data structures and stuff. Like, heap allocation should be avoided at all costs. So in general, inserting into arrays is very slow. The same is true of removing for the same reasons. Because if I remove the first element, then I have to shift everything else to the left by one. So that's order in. And the next is find, which usually is order in. If your array is sorted, then yes. Right, but then you have wasted memory. Because whatever sort of memory manager you're using to control your heap space says, okay, I have this array allocated that's 6 blocks, but now it's just 5. And that's fine for one element, but if you're removing half the array, then you're wasting a ton of space. So in general, you have to shift. Finding is just if your array is completely unordered, you have to go through every element to see if what you're looking for is there. So that's order in. If your array is sorted, you can do sort of a classic binary search, which would be log in. But general case is ordered. Arrays are not great when you're trying to find stuff. Or in general, just store elements that have sort of an inherent order to them. Okay. Next is linked lists, which are very similar to arrays. They sort of just store an ordered collection of data of a single type. But the fundamental difference between linked lists and arrays is that linked lists are not stored contiguously. Linked lists are often represented graphically as sort of a chain of nodes, where, say, I have the elements 1, 2, and 3, and then each node is at a separate place in memory and points to the next node in the list. This is called a singly linked list, where each node points to its next one. You can also have doubly linked, where each node also points to the one behind it, which can be useful for certain like traversal algorithms. But in general, these are very, very similar to arrays. The key difference is that getting an element becomes order in, because this is not a contiguous block of memory. We can't just do pointer math and get to the right place. So we will, just like an array, we will have a pointer to the first element, but we can't just increment that pointer to get to the second one. We have to follow the pointer that node points to, and then we get to the next node. So getting an arbitrary, like a value at a given index, which is very common in an array, is very expensive in a linked list. And I'll talk about sort of a workaround to that in just a minute. Everything else is actually the same. Insertion is order in, which is the same as an array, but for different reasons. The reason that it's order in is because you have to first get to the element that you're trying to insert after. But once you're there, say I'm trying to insert between 2 and 3, no shifting has to happen, because these aren't contiguous in the first place. All I have to do, say I want to put 4 in here, is just delete the pointers that are already there, just sort of reshape it. So inserting can be fast if you don't have to do the order in traversal to get to the place that you're trying to insert at. Removal is exactly the same thing. It's order in because you have to get there, but once you're there, it's just exchanging pointers to actually remove it. And then what else? Finding, exact same thing, order in. Now, something that I have used in the past, I'm not sure if this is a common thing because it does take up more space than another data structure would, is I just call it like an invasive linked list, where if I'm storing, if the nodes, if the type of data that I'm storing in the node is like my own type, like in this trivial example, I'm just storing integers. But say I'm storing some structure, I'll just do C++. Say I'm storing, okay, I can't erase that. Some struct S. And this has a bunch of stuff, like whatever. It's a big structure. Then I will also store a pointer to the node in the list that contains this object. So what that would look like if instead of 1, 2, oh my gosh, instead of 1, 2, 3, 4, if I had like S1, S2, and so on, S1's node pointer would go there. And what that means is if I have a particular object, I can get to its place in the list in constant time, because that's just following a pointer. And at that point, I can do whatever I want with it. Insertion and removal, because I don't have to do the order in traversal to get there, those become constant time. So that's sort of a weird case that can be useful, but I'm not going to talk a whole lot more about it because it's not part of the like traditional linked list implementation. Okay, next is trees, which are interesting in that they can be implemented in 2 ways. Well, many ways, but we will be talking in particular about binary trees. So this is just a tree where each node has between 0 and 2 children, inclusive, of course. And these can be implemented as arrays or in a similar way to linked lists, but not quite the same. So that's the one we're going to look at first, because that's like the more traditional way of implementing a tree. That's sort of also the more common way. So in this sort of model, each node is just like a node in a linked list, except that it stores not just one pointer to its next element, but pointers to its child elements. So we would often represent a tree like this, where I have some elements A, B, and C in here. And then if A had a child, D, that could go there. If D had a child E, that would go there. So each node only knows about its children. You can obviously design it so that each node also has a pointer to its parent, which can be useful, but sort of weird. But in general, this is a very, very, very useful structure because the sort of way I've drawn it graphically hopefully can help you visualize that. But it's just whenever you need to store data that is not only ordered, like not just talking about like a set of integers that is ordered, but data that is sorted hierarchically. That's what a tree is used for. And you can use them to just order a list of events, that's fine. But when you're sort of using trees to implement your own things, anything where there's like an inherent parent and child relationship, it's basically always going to be done as a tree. It's just very useful. Okay, so in this tree sort of model here, in this like node pointer model, common operations of get. So if I want to see if a particular value is in here, that becomes order log 2 of n. And that 2 is just sort of implicit. True, exactly. Yeah. I think it's easier for people to make the connection as to why does log show up there if I show the 2, because each node has at most 2 children. Yeah. So you can think of this as if the data in my tree is sorted hierarchically, which is what it's used for, and I'm trying to get a certain element, I'm trying to find something, then at each step, I can basically eliminate up to half of the elements in the tree. And the reason for this is like the typical ordering is, say, on the left here, I have everything that is less than B. And on the right, I have everything that is greater than B. And so if I just sort of fill this out with some more elements, just like as dummy elements, say I am looking for E. So I'll go to my root. So the sort of starting point of any tree is the root. That's the only node that traditionally that you store a pointer to. So you always start finding things from the root. Okay, I'm looking for node E. Well, based on this, just this sort of fake order I've come up with, E is less than B. So I know it's going to be on the left side. So I don't even have to search any of these. That's half the tree. I come here, I say, okay, A. Well, I know that E is less than A. And if A did have stuff, I wouldn't even have to search that either. But in this case, it doesn't. So that doesn't actually help you out. Then I go to D, I say, okay, E is greater than D, so I don't have to search whatever is less than D. And then finally I get to E. And the reason that's log 2 is the way I like to think of logarithms, and I won't go too far into it, but basically we have addition and then multiplication, where multiplication is just like repeated addition. It's just adding something over and over. Then we have exponentiation, which is sort of like super addition. It's like a weird sort of thing, but it's very similar to addition, where you're just compounding values over and over again. In a similar way, we have subtraction, where it's just adding a negative number. And then we have division, which is somewhat analogous to multiplication. You can multiply by the inverse. And then we have like super subtraction, which is a logarithm. And it's sort of a recursive subtraction. And it's a recursive division, I guess is a better way to think of it. Because at each step of this tree, I can divide the elements that I have left to search by 2. So I cut it in 2 every single time, and that's approximately log 2. Okay, so that's get and also find. It's the same operation in a tree. Insertion, that's just going to be log in as well, because all I have to do is find, okay, is the element I'm inserting less than B? Yes, go here. Is it greater than A? Yes, put it there. Good. So every time you cut it in half, yeah. Good question. Okay, so I'll repeat that for online. The question was, because the time complexity for this stuff is log of n. You don't have to worry about sorting them. So the worrying about sorting them happens at insertion. Because we could just say for insertion, okay, like just make this new thing my root. That's constant time because I already have a pointer to the root. But instead, we go through starting at the root and see where it lies in the tree based on whatever order we've specified. And so whenever we insert, we are inserting it in such a way that the tree remains sorted, which allows us to have this log in find. Yes. What if C was less than B? In that case, C would just be on the left side. If both A and C were less than B. So if C is greater than A, then C would be right here because it's less than B, but it's greater than A. If C was less than A, then it would go to the left, and it's a recursive process. So if C is less than D, then it goes here. If it's greater than D, it goes here. If it's less than E, it goes there. Greater, it goes there. So in general, that process of inserting things and sorting them in the order that they are added to the tree can lead to like sort of catastrophic results. If you give it a particular set of data that is ordered in a certain way, you can just end up with these big long chains where nothing is actually divided out. Each node only has 1 or 0 children. And at that point, you just have a linked list. That's just order in, because whenever you search, you cut whatever is off, you cut off whatever is on the other half of the tree. Well, there's nothing there. So you're not actually saving time. But usually that doesn't happen. Okay, and then removal is also log in, just because we have to find the element, remove it. And there is a bit of an extra step, which is just picking which of the 2 children to sort of move up into the current slot. But that's pretty simple and just an implementation detail, so I won't really talk about it. Okay, so those are the 3 like fundamental data structures. And the thing to note about all of them is that in their own ways, they are all ordered. Not meaning that the data they contain is sorted, but an array is ordered just because it's all right next to each other in memory. A linked list is ordered just because each node points only to the next node. A tree is ordered in sort of a weird top-down hierarchical way. And also usually it's sorted as well. But some of the more complex data structures are not necessarily ordered. It's just like, they're just, an element is part of this thing, but we don't care where it is relative to the other elements in it. Okay, so all good on those. Any more questions on array, linked list, or tree? No? Awesome. So the first ones we will be looking at are both very simple and both very similar. This is the stack and the queue. The queue you should, or sorry, the stack you should already be somewhat familiar with because we've talked about the hardware stack, which is that thing where like we represent method calls as a series of stack frames on the stack, and you push to the top of the stack, and then when a method is done running, you pop from the top of it. That's all a stack is. And a queue is sort of the opposite. I think I'll do them in like a side-by-side actually, because they are very similar. So a stack is usually implemented as an array. A queue is usually implemented as a linked list. The operations, for some reason, the like common operations on these two have particular names, not just like insert and get and stuff. So I'll define those. So stack, like, no, I'll do that in a minute. I think I'll first talk about the order that their data is stored. So stack is what's called a LIFO, last in, first out, and queue is a FIFO, first in, first out. So stacks are often represented as just sort of a flat baseline, and then you add things to the stack. So if I have a stack of integers and I push 1, then I push 3, then I push 5, it would look like that. It's just a very nice way of graphically showing that. And then whenever I want to remove, we'll note that every time I add, I only add to the top. That's sort of one of the main things about a stack. I can't add anywhere in the middle, I can't add at the bottom, only at the top, which corresponds to the end of the array, which is important. Because remember, there's that special case about inserting into an array where if I insert exactly at the end, I don't have to shift anything. So it's usually constant time unless I have to resize my array, which is very slow, but it evens out. And then the other part about it is when I remove an element, I only remove from the top of the stack. So if I remove, and then whatever was removed is the value that's returned. If I want to get the value that is on the top of the stack without removing it, that's also an operation called peek. So peek we can think of as analogous to get. And then pop is where I remove something from the stack, which is analogous to remove. And then push is where I put it on top, and that's insert. And all of these are order one, amortized order one. Amortized meaning it averages out over all the invocations of these methods, because sometimes there are those cases where I need a bigger array, all that stuff. So that's really all you have there. There isn't really a find. Like find operations don't really apply to stack and queue. You would just never do that. I mean, you could because it's just an array and a linked list under the hood, but you would never do that. In a queue, it depends on the language. The sort of method names are less formal. For a stack, this is basically always the case, but for a queue, you might see like first or like front. I think in C++ it is. That's get. And then removing, you would have like DQ. And then to add, you might have in queue for insert. Okay, so a queue is ordered in sort of the opposite way of a stack, where rather than adding to the top of the stack, the end of the array, we add, rather than removing from the top of the stack, we remove from the end of the queue. We still add to the end. No, wait, I'm messing this up. Okay, let me just draw it. So if I have this example that I had with the stack, 1, 3, 5, notice the order I inserted them in. I started here, and then I always add to the end. So adding to the queue, appending to it, is the exact same as the stack. It's just a different data structure. We always add to the end. But when we remove, instead of removing from the end, removing from the top, we remove from the front. So if I call this queue.dq, I'll get rid of that one, and then the pointer now points to that. That's the head of the queue. Then I remove that one, and the pointer now points to that. Okay. So these are also all order one. The reason insert is order one here, this really should be order in, because like in just this model here, where I only have a pointer to the front of the queue, if I want to add something to the end, I have to start at the front, go all the way to the end, and then add it. But the way you get around that is just by maintaining a pointer both to the head of the queue and the tail of the queue, so that you can both remove and add in constant time. And again, the concept of like sorting this or searching it doesn't really exist. Okay, I think that's all I wanted to say about those. Unfortunately, these aren't particularly useful. I just like the stack is useful for understanding the hardware stack, I guess, but it's very simple. The queue is very simple as well. You just don't really use them that often. But any questions about them before we move on? No, great. Okay. So a more interesting one is called a priority queue. And priority queue is sort of an annoying name because it is a queue in a sense, but it's not a queue that's related to the queue we just looked at. So in a regular queue, the reason it's called a queue is because it's like a line. Like if you're in line getting lunch or something, you start at the back of the line, and then the first person to leave the line, to get removed from the line, is standing at the front because they were there first. A priority queue is similar to that, except the first person to get removed is not necessarily the first person who was there. It's someone who has some external like priority value assigned to them. And because of that, this is a hierarchical ordering. We have some type of arbitrary value that is assigned to the type that we're storing. And we need it to be ordered, because if we want to remove the element that has the highest priority, that should just be at the top of the queue. So this is a tree, usually implemented as just a binary tree. And further to that, it is sometimes also implemented as an array-based tree. And this is the other type of tree I didn't talk about. I talked about node-based one, where you have nodes that point to their children. An array-based one is sort of interesting in that you still have this concept of each element has at most 2 children, but it's all stored contiguously. So it is more cache friendly, not as many pointers going around. Instead, children are assigned based on an index in the array. So the root will always be just the first element, the index 0. And then the left child will be, say, this node, and the right child will be this one. And then this, the left child of the root, will have a left child that is here, and a right child that is here. And then the right child of the root will have a left child that is all the way at the end, and then a right child that is the way down here. And then it just sort of keeps going like that. So the formula for a left child of, yes. Mhm. Right. Sort of, but the distance between them grows as you get further and further down the tree. Yeah, it does depend on the level, exactly. Because each level, if you draw it graphically, each level will have more and more nodes on it, right? Yeah, exactly. So the left will be like the index of the left child of a given node at index I will be at 2i plus 1. And then the right child will be at 2i plus 2. And you can sort of go through this and validate that it works out there. And this is good because all the nodes are guaranteed to be right next to each other. It's an array, so it's all stored right together. You're going to have less cache or fewer cache misses. So this can be faster. And for some reason, priority queues are just, at least from what I've seen, are often implemented as array-based trees, where usually just in general, a binary tree is implemented as a series of nodes. But this is more complicated, especially because it's a very, it's a more general data structure. It's one where, unlike a, well, I guess that's not entirely true. But the sort of ordering of things is more complicated than just in a regular tree. All we really care about, in sort of a very simple sense, say we're just dealing with integers. We might have, say, like this tree here, or this heap here, priority queue here, which, if you look at that as a binary tree, that ordering doesn't really make sense. But all we care about is that all elements below a given element have some particular relationship to that element. In this case, I've done it so that everything below each element is greater than that element. So this would be what's called a min heap. So priority queue, also called heap. And a min heap is one in which the minimum element in the entire collection is always the root. And a max heap is sort of the reverse, where the greatest element, by whatever measure you assign value, will be the root. And that's useful because in terms of its use as a queue, you're only interested in removing the thing with the highest or lowest priority. That's order 1, because it's right at the root. You know exactly where it is. It's pretty easy. Okay. Now, I can talk a bit about min heaps in particular. This is actually where the terminology for like the heap, what I refer to as the heap, that area of memory that is dynamically allocated into. It comes from Java, heap, and C# I think uses the same thing. C++ a little bit, but not as much. I believe the reason, this is more theoretical, but something that I've pieced together from various things that I know exist and that I have looked into. Java and C#, they implement some type of reference counting system where a reference, really, this should be called a pointer. So as you know, in C++ and C, whenever you allocate something on a heap, you are responsible for deallocating, which is not like a stack variable, because when you allocate something on the stack, whenever the method that you're in, whenever that stack frame is popped off of the stack, that variable is just gone. It's deallocated automatically. In the heap, you're responsible for doing it. And it can be very tricky to keep track of that. And so you end up with just unused memory on the heap, which you maybe just never delete, or even worse, you think you delete but don't, and so you don't even have a pointer to it. You can't go there and delete it. It's just that the sort of internal memory management system thinks that you're using it, but you're not. And so Java and C# sort of solve this problem by making it so that you don't even have to delete yourself. They use reference counting to implement something called garbage collection, which is just sort of a process that runs in the background. It's like part of the runtime of the language that will clean up these pointers for you. And the way that it determines whether or not a pointer can be cleaned up, because it's not going to go and delete something that you're using, right? That wouldn't work. The way it determines whether or not you're using it is by reference counting. So reference counting is just a way of assigning to each pointer that points onto the heap a number, a positive integer, that represents the number of places that that pointer is referenced in the code. And so in C++, they have actually implemented this somewhat, reference counting, just not garbage collection. It's not, well, it sort of is automatic, but that would be in the shared pointer class, which is just a wrapper for a pointer. I don't want to get too far into C++, but it's a template struct. You'll have a pointer to some data on the heap, and then you'll have this like additional structure used for reference counting. And because of the way C++ works, if you pass a shared pointer to a function by value, so you copy that, the little internal reference counting mechanism in here will say, okay, I've been copied, so I'm now referenced from another place in the code. So I'll increment the reference count. And then when a shared pointer is destroyed, when its destructor is called, it will check its little internal counter. And if it's 0 now, it will deallocate itself. Because if it's not 0, it means some other place in the code has this pointer, so it's being used. But anyways, that's in C++. Java and C# implement a very similar thing under the hood. And my suspicion is that they store these in a min heap where the condition, or sort of the way that priority is assigned is based on the reference counter, the number of references that they have. So if I have an object that has 0 references, and I have one that has 1, one that has like 3, maybe this one has 4, whatever, every so often, whenever the garbage collection mechanism background thing runs, it'll just pop everything off the heap as long as the root is 0. Because every time you pop, it gets sort of reordered so that the minimum is once again at the top. And while that minimum is 0, you know, you are looking at pointers that you know, are pointing to memory that is allocated on the heap, but is not being used. So that's sort of something I've pieced together. I'm not sure if that's actually true, but that certainly would be a way to implement a very primitive garbage collection system on your own if you wanted to. Okay. And heaps are useful in other ways. There's an algorithm called heap sort, where basically you just take an array of data and you throw it into a heap. And because when you insert into a heap, it like orders itself, you then just pop everything off the heap until there's nothing left. and every time you pop, it sort of reorders itself so that the minimum is at the top. So you can sort in login time using that, but we'll talk about that later. Okay. Next is a hash table. These are also called dictionaries. Newer languages have these as like primitive types. Python in particular has dictionaries. JavaScript, like objects, are just big hash tables. But really what it is it's just an array with some additional like weird and very complicated conditions on how things are inserted into the array. So it's built on an array. But the interesting part about it is the hashing function. So a hash function is something that takes some object, something, and it spits out a number. That number will usually be unsigned. It'll usually be 64 bits. Not really important. The point is that if you have a good hash function that you can just give some object, the hash function will spit out an almost unique and basically mathematically a unique hash value for that particular object. So like a concrete example of this would be if I have the string A and I have the string AA, even though those are very similar strings, they will still have different hash values. And the way that these hash functions are written is super complex. I really don't understand it. A lot of it is like cryptography and stuff. But for very primitive types, they're like trivial. Because if I have like, if I'm trying to define a hash function that hashes some integer, well, each integer is already its own like unique value. So I can just return the integer. Same for the float and double. Like those are, I'm not sure, there might be some weird edge cases, but it seems to me that you could just return whatever bits make up that float or double as an unsigned 64-bit integer. And there you go. And it'll be unique to that particular value. And so what these do, or how these are used rather, is when you have a hash table, say I have an array of length n, and I want to insert this element. Say I want to insert these two strings. So maybe this has a hash value of 95, and this has a hash value of 1002. So if I want to insert just A, then I will look at its hash value. So that's 95, and I will mod by the number of slots I have in my table, which is n. So in this case, I have 1, 2, 3, 4, 5 slots. So 95 mod n just happens to be 0. So I put single A there. Now, if I want to do double A, that'll be 1002 mod 5, which is 2. So double A would go there. Problems occur if you have collisions. So say just randomly, I have another string BB, which is also 1002. Then that wants to be inserted here, but there's already something there. And there are various algorithms that determine where the next best place to put it is. The simplest one is to just look, like just check each next element until you find an empty spot. There are several ways of dealing with this. We're not really going to get into it. The main thing to notice, or the main advantage of hash tables, is that in general, all the operations on them are constant time. These things are basically just magical structures that you can put data into. And if you want to check if that data is there, you can do it in constant time. They're not necessarily sorted. That's another important thing to note. It's not some super crazy sorting algorithm that does this. It's just, it relies on you having a good hash function. And for all those sort of built-in basic types that you would ever use, like string and integer floating types, those will generally have predefined hash functions by your compiler vendor. And so you just assume that it is good. Did you have a question? Sorry? Right. Yes. So it's average case constant time. It's amortized. That's what they call it. Because, huh? Well, it depends on your collision resolution, which I can talk to you afterwards if you're interested, but I'm almost out of time. The question was, if I had a collision and I had to put BB here, and I go to check if BB is there, and I look there and I say, oh, well, that's not it, then how would I know if it's still there? And that depends on the implementation, but a good question. But in general, get/find are order one, because all I have to do is take the thing I'm trying to find, feed it into my hash function, which, if it's a good one, the value that it spits out will be basically unique. And also it won't take super long. So you sort of assume that that is also constant time. And then I just have to go to that index in the table. And if the thing is there, then it's in the set. So that's all I need to do. Insertion is also order one. All I have to do is find the hash function, do some math on it, which is constant time, put it in the right spot, again, until I find a collision, but amortized order one across all things that I insert into it. Assuming I have a decent hash function, this will be constant time. And the same is true for removal. Because all I have to do, get the hash value, go to that place, and remove the thing from it. Just set it to some like empty value, whatever you specify. Okay, so that's a hash table. I think I'm going to end there because I don't have time to talk about the rest of this. There are just two things left, but each of them has sort of two components. And I can finish off next time talking about those. So what we have left is sets, which are basically, they're very, very simple. They're basically just mathematical sets, but there are tree sets and hash sets, and those are both useful, both different. And then also there are maps, which are the most useful. And there are also the tree and hash maps. So we will talk about those at the top of next time. Other than that, next time, I think we will start getting into, we might look at some common algorithms on these. I'm not sure. I'll have to try and figure out, because I don't want to just show you a bunch of stuff for no reason. Like I ultimately what we're going to be doing is looking at creating our own data structures by composing these existing ones, and then writing algorithms that operate on those structures. So if there are any like simple algorithms that are common that I might reference when we're making our own, then I'll look at those, but I don't want to just hit you with a bunch of sorts because you'll just learn those in class. But yeah, thanks for coming out, and I will see you next Thursday.